look at a solar panel and just wonder, how does that thing take pure sunlight and turn it into actual electricity? Well, today we're going to pull back the curtain and see exactly how that magic happens.
All right, to get started, let's kick things off with a really cool puzzle. Picture this. You've got a single LED, right? A light-emitting diode. Now, we know if you shine its light on a solar cell, you get power. But here's the twist. An LED is pretty much a solar cell running in reverse. So could it create enough of its own light to power itself? You know, like a perpetual motion machine of light? On the surface, it kind of feels like it should work, but we're going to find out if the physics actually agrees. So to even begin to answer that, we've got to get back to basics. We need to understand the fundamental science here. Let's start at square one. How on earth does light become electricity in the first place?
Okay, so the secret sauce here is something called the photovoltaic effect. And the name actually gives it all away if you break it down. Photo, which means light, and voltaic, which relates to voltage. It's literally light creating voltage. Just picture these tiny energetic particles of lights, they're called photons, slamming into a surface. If a photon has enough oomph, it can physically knock an electron loose from its atom. And that free-roaming electron, well, that is the very beginning of our electrical current.
Now, here's where it gets really interesting. When that electron gets knocked out, it leaves behind an empty spot. Scientists call it a hole. Just think of it like popping a piece out of a puzzle. And just like magnets, that negatively charged electron desperately wants to snap right back into that positively charged hole. So the entire genius of a solar cell is to build a system that can catch that electron and whisk it away before it has a chance to go back home. Okay, so that's the basic principle, the physics behind it. Now let's see how engineers take that concept and build it into the actual thing we see on rooftops, the solar cell itself. So you can really think of a solar cell as a kind of high-tech sandwich. You've got your top layer of glass for protection, then an anti-reflective coating to make sure as much sunlight gets in as possible. But the real meat of the sandwich, the most important part, is the metal grid on top that collects the electrons. And right underneath that, the layers of silicon. That's the engine room. That's where all the action happens. And this right here is a perfect example of the engineering puzzles solar designers face. You see that metal grid on top? It has to be there to collect all those freed electrons. But every single line of metal also casts a tiny shadow on the silicon underneath, blocking the very sunlight it needs. It's this incredible balancing act. Make the grid thick enough to carry the current, but thin enough to let the light through.
Okay, we've seen the big picture, the layers of the sandwich. Now it's time to zoom in. I mean, way in. We're going down to the atomic level, inside those silicon layers, because this is where the real heart of the technology beats. So, the big secret to making all this work is that the silicon isn't actually pure. It's been intentionally messed with in a process called doping. They take one layer and dope it with phosphorus. Now, phosphorus has an extra electron, so this creates a layer with a bunch of spare, free electrons. We call this N-type for negative. Then they take the other layer and dope it with boron, which is missing an electron. This creates a bunch of empty spots, or holes. And you guessed it, we call that P-type for positive.
Okay, so now we have our N-type and P-type layers. The crucial part is what happens when you press them together. Right where they meet, they form something called the p-n junction. It's totally natural. Some of those free electrons from the N side immediately jump across the boundary to fill the holes on the P side. This little migration creates a permanent one-way electric field right at the junction. It's like an invisible slide that only lets electrons go in one direction.
And here it is, the payoff for all that setup. A photon of sunlight comes in and bam! It hits an atom right in that junction and knocks an electron loose. Instantly, that one-way electric field, that slide we just talked about, springs into action. It shoves the electron over to the N side and pushes the hole over to the P side. It forces them apart. And that separation of charge, that's it. That's what creates voltage.
It's just amazing, right? That is a ton of physics happening at a level you can't even see. So let's zoom back out now and look at how we take that tiny atomic level spark and scale it all the way up into a system that can actually power your entire house.
All right, get ready for this, because it's a fact that surprises a lot of people. A single solar cell produces only about half a volt. That's it. And it doesn't matter how big you make it. A giant cell and a tiny cell both produce about half a volt. Now, making the cell bigger does give you more current, That's the flow of electrons. But the electrical pressure, the voltage, is stuck right there at 0.5 volts.
So obviously, to get any kind of useful power, you have to wire a bunch of these cells together. And there are two main ways to do it. You can wire them in series, which is like stacking batteries end to end. That adds up all the voltage. Or you can wire them in parallel, which adds up all the current. Real-world solar designers actually use a combination of both to build a panel or an array with the exact electrical characteristics they need.
But a complete solar system is way more than just the panels themselves. You have the solar array, sure, that's what's making the power. But then you need a charge controller to manage that power and protect the battery. The battery is where you store all that energy for when the sun isn't shining. And then there's one last absolutely critical piece of the puzzle: the inverter.
So what's this inverter do? Well, its job is to convert DC power into AC power. See, the power that comes from your panels and batteries is direct current, or DC. You can think of it like a river, where all the electrons are flowing steadily in one direction. But all this stuff in our homes, our appliances, the grid itself, that all runs on alternating current, or AC. That's more like the tide, with the electrons flowing back and forth. The inverter is the magic box that acts as a translator, turning that DC river into the AC tide your house can actually use.
Okay, so now we have a complete system, from sunlight to your toaster. But if you've ever glanced at the spec sheet for a solar panel, you know they are nowhere near perfect. So let's talk about the reality of how efficient these things really are. I'm sure you've noticed that not all solar panels look identical. You've got those common bluish ones, the ones that have that kind of sparkly, flaky pattern. Those are polycrystalline. They're generally more affordable, but also a bit less efficient. Then you've got the really sleek, uniform black panels. Those are monocrystalline. They cost more, but they can squeeze more power out of the same amount of space. It's always a trade-off, cost versus performance. So that begs the question, why aren't they 100% efficient? Why can't we capture all of the sun's energy? Well, it really just comes down to physics. The material itself, silicon, has a hard theoretical limit. A huge chunk of light is simply the wrong wavelength. It either doesn't have enough energy or it has way too much, which just turns into heat. Then you factor in some reflection off the glass and other small losses, and you end up with a modern panel converting only about 20% of the sunlight into electricity. And that brings us all the way back to our little puzzle from the beginning. Can an LED power itself with its own light? Well, now we have our answer. And it is a definite, resounding no. Because of all those efficiency losses we just talked about, an LED acting as a solar cell can only convert maybe 10% of its own light back into electricity. The laws of thermodynamics just don't play that game. You'd actually need the light from about 10 other LEDs just to power a single one. So when you think about it, the entire modern solar industry is built on this one amazing, versatile, but also fundamentally limited material: silicon. It's the element that brought solar power to the masses. But knowing its physical limits, it leaves us with this massive, exciting question for what's next. Silicon got us here, but what material is going to power our future?